Hey folks, Todd Coburn here with your Aerospace Structures series. This lecture is for statics, and what we're going to cover is the idea of couples. The moment caused by two forces when they're parallel, equal, and opposite, and spaced at some distance apart. This applies to our study of rigid bodies and how these respond to external forces. Let's see how it works. So once again, we're studying couples and force couple systems. And just one word to clarify, we need to understand that this is not what we're talking about. Not this kind of couple. We're talking about a different kind of couple. We're talking about not a couple in love, but when forces are not in love, kind of the opposite. All right, so what we're talking about here is forces, two forces. Now, if these forces were in love, this couple would be going like this in the same direction, but as so often is the case, they start out like this, and after a while they're like this, and then they get further and further apart. Not only are they going in different directions, completely opposite directions, but they ain't even close to each other, they're getting further and further apart. And that's kind of the idea of a couple. If we have two forces, they are equal and opposite, and they are separated by some distance, we're going to find that the moment caused by those forces, we're going to find out that these forces cause a moment. Now, anytime we have a force, that's just it's going to cause translation, F equals ma. If we have a moment, it's going to cause angular acceleration, which is m equals I alpha, right? If we have a force, it's causing a translation, and yet if it's at any distance from a point, we saw that it causes a moment as well. The magnitude of that moment was r cross f. That's the moment. Now, if we have two forces, and they're already parallel, equal and opposite, and parallel at some distance between them, then the moment caused is a pure moment, and it is equal to the magnitude of the force times the perpendicular distance. And that's what we're going to be studying today. So we have a force F and minus F. They are opposite in sense and parallel. We know that we can calculate the moment about any point by taking the r cross F. Since we have two forces, we're going to have two r cross F's. If we have these forces spaced as shown in this lower figure here, we have the first force, the moment it causes around O, will draw any line from O to any point along the force vector. We're going to choose point A in this case. RA, which is, we could call the vector OA with a little line arrow over it, right? That distance crossed with that force vector will give us the moment that force causes. Of course, the other force, that minus force, which is just a force in another direction, but since it's the opposite direction, we call it a minus of the other force magnitude, right? We can take a line, a vector from point O, which we want the moment about, to any point along the vector. Let's just choose point B for fun. That line segment, OB, crossed with that vector minus F, will give us the moment that it causes about point O. The resultant moment about O will be RA cross F plus RB cross minus F. That's the total moment about point O, as you see with the green moment vector. Now, this moment vector is shown with a single arrowhead, but actually it's good practice and more common to show moments. This is we're showing that it's a moment, but actually usually what we do is show a double-headed arrow. That shows that that's a moment. A single-headed arrow is a force. That is a force. That is a moment. Double-headed arrow is a moment. Got it? Okay. So we're going to call these a couple. So we saw here the moment is then, the vector moment is r cross f plus r cross minus f. Now, because the operations of vectors that we saw before, we can write this is r cross f plus minus r cross f, right? We can just move that minus sign, no problem. Which means we then can separate this due to our rules of operations. We could say RA minus RB cross F, okay? Where that RA is a vector minus RB the vector cross F. Great. This means this will give us this R. So if we did this R, now taking a look at this, RA minus RB is just that vector RA, which has an IJK component, minus that vector B, which has an IJK component. So the resultant RA minus RB is just the blue vector R, going from point B toward point A. So the moment about O for this couple is RA cross F plus RB cross minus F, which is equivalent to this vector R, which is between them, crossed F. Okay, got that? Hold on to that thought. Now, remember that the scalar magnitude, we said, by definition, was just RF sine theta, where r sine theta is simply the perpendicular distance between these. So focusing on the plane that the two vectors lie in, we see that this r, which is RA minus RB, lies in that plane, and the r sine theta component is just the perpendicular distance d, which means the magnitude of that moment is just that force multiplied by the perpendicular distance. Now, we're still doing a lot of cross products here. However, when we understand this principle, we're going to find out we can do a lot of completely accurate calculations with moments once we understand this couple idea by just taking scalar operations of the force and the perpendicular distance between these two forces of the couple, okay? So the moment is just RF sine theta, was just FD. It looks like this. These two forces of the couple are lying in a plane, no matter what they are, since they're parallel, no matter what their orientation, if they're parallel, they're gonna form a plane, and the moment will just be the F times the perpendicular distance between them, and it will be perpendicular to the plane that they lie in, as we see here with the green moment vector. Once again, that really should have a double arrowhead. Okay? Now, we should have also learned, remember, forces are vectors. We call them bound vectors because if you move a force, when you move a force, you generate a moment. When you move a moment, you don't have to do anything. It doesn't generate anything. Therefore, forces are called bound vectors and moments are called free vectors. It's kind of like forces are like if you live in a place where you have to pay off the government to move. I want to move over to this place over. Oh, you have to pay somebody off, get somebody to pull some strings. You have to get their permission. It's a bound vector, bound society. Moments are like Americans. You can live wherever you want. You don't like living here, you move. You don't like living there, you move. You don't have to buy anybody off or talk to anybody. You just go. Forces are bound vectors. Moments are free vectors. We can apply them. Once we calculate that moment, we can move it anywhere. Now, I say we can move it anywhere, but this moment, actually, we can't change its sense. It just doesn't matter any longer where we place it. As long as we keep the vector the same way, we can place it anywhere. It has the same effect on the part. Not so the force. If you move that force, it's going to change other things among the part. Okay, so we can say that two couples will have an equal moment if the FD equals the FD. Well, duh, that makes sense, right? So if we have two forces, so that means if we have two forces of a couple and they're a certain distance apart, right? If another set of forces have the same moment, we say that the couples are equivalent. So that means if we have a force here at a distance, let's say it's a force of 100 pounds times 1 inch. If we have 2 inches between another set of forces, then if those are half the magnitude, then you could end up with the same couple effect. Okay? All right. So two couples will have equal moments if the FDs are the same, if the two couples lie in parallel planes. If they don't lie in parallel planes, then actually they will have it's actually a different moment, has different vector direction, right? And if they have the same sense or cause the same rotation. For example, if they both cause a right-hand rule kind of rotation, if the other one causes this rotation, then they ain't equivalent. Okay. So we can add these together also. For example, if we have couple F1 lying in plane P1 and couple F2 lying in plane P2, we can then look at the moments of each, the R cross F of each. So let's consider that. And our resultant will just be the R cross the resultant. So we can either take the R1 cross F1 plus R cross F2, or we can take that R cross the resultant, right? Back to the basic properties of a vector with Varignon's theorem. Okay? Seems kind of trivial, but that's true. All right. So once again, we see here, we have a couple can be represented by a vector with a magnitude and direction equal to the moment of the couple. For example, here we see in figure A, we have a couple lying in a plane. If we know what the magnitude of the force is, we know the magnitude of the distance between them, the perpendicular distance, then actually the moment is just FD, as we can see here. Once again, this is shown with a vector, an arrow with a little circle around it. That's another way of showing moments. We could have simply shown that with a double-headed arrow. Okay? And we can see now that that's a moment, we can place it anywhere without affecting anything. So actually couples are actually, whenever we have a couple of forces, that actually gives us a moment that's a free vector. So we can actually show it like we see in figure C, or we can show the components mx, my, mz by just projecting that vector m onto the axis. What that means is we just take a m dot x, the unit vector, m dot I. M dotted with the unit vector I will give us the moment about I. M dotted with the unit vector y gives us my, or j. M dotted with the unit vector j. M dotted with the unit vector k. Well, you think, wait a minute, if you understand dot products, you say, wait a minute, when I take the dot product, all it does is give me back that one component. Yes, that's true. If we already have this vector written as a mxi plus myj plus mzk, then actually this dot operation will simply just give us back those components. And so couple vectors obey the law of addition of vectors. Great, they're free vectors. We talked about that. And they can be resolved into perpendicular components. Okay. So let's say that we want to, so now we're going to learn a couple tricks that we can do when we're evaluating vectors. For example, let's take a rigid body, this gray brownish body, and we have a force applied to it. Now, we can calculate the moment around some point O. Why would we do that? Well, usually we do that when we have found that the center of mass is at point O, and now we want to understand what all these forces are causing. Are they causing translation or rotation? Right? So when we take dynamics, we'll do a little bit with the dynamics piece of that, looking at the sum of m equals I alphas, the sum of the forces equals MAs. So usually we would do this with respect to the CG, or the center of mass. But let's just keep the arbitrary case here. We have a force applied. It's applied somewhere on the part at point A here, and we want to know what the moment is about point O. Well, we just draw a line, a vector, a position vector from O to A. We can call that vector OA, or in this case it's called R. And we're going to cross that with our vector force F to get the total moment. Now, we could, if we want to write the equivalent forces at point O, what we would do is we would just, one way to do this is just to say, well, we have this thing here, and we have a force here, F. If we want to go here to point O, what we're going to do is say, well, the equivalent set of forces then will have a force, or actually, let me do it this way. It's equal to a force here in the same exact direction and a moment, which I will draw like this, which is simply the R cross F. That will perfectly, so this force causes both a translation of O and a rotation about O, and if equivalent to this system where we have a force here and a moment here. But the question is, why is that? How do we know that to be true? Well, one way that we can figure that out is by applying what we've now learned about couples. Let's take a look at this. So what we're going to do is say, okay, if we have a force here, let's go ahead and we know that we can take, at any point, we can place something that's equal and opposite. So let's go ahead and do that. Let's apply a balanced force at point O, and let's make it equal to F. So what we're going to do is put a force that's exactly equal to minus F at point O and exactly equal to plus F. Since plus F and minus F has no net, the net of that, the summation of forces in that skew direction that we're pointing at is 0, and this has no effect on the body at all. We then can cancel. We take a look and say, wait a minute, this F and this other F form a couple. The blue F stays there, and then the minus F and the plus F, instead of canceling the minus F with the blue F, we can cancel the minus F with the red F. But we also recognize that F minus F, the red F minus F, is actually a couple. And the magnitude of the moment is just F cross R, or R cross F, or you could say that it is FD. So actually, now we can replace that couple with the moment that's equivalent to it. Once again, we can write it as either R cross F or as FD. Magnitude FD with, if we can figure out what the direction is, and we see that now we have an equivalent system. So we see that indeed we can either write the thing this way, F at some point, and that is equal to a force in a moment. Now, if this were truly the CG of the part, that would allow us to now, once we've taken dynamics, to calculate what the acceleration is in the translational direction and what the rotation is, the angular acceleration. That is what you're going to learn to do in dynamics. If you don't learn these principles now in statics about how to do these couple forces systems, then you will be ill prepared to take dynamics. You will crash and burn. It's important that you master these basic fundamentals so when you get dynamics, you can just learn the little baby steps forward for how we're going to turn that into accelerations, both translational and rotational. Got that? Plus, you need to master this in order to do meaningful structural analysis of aircraft and rockets. Got it? Okay. So those are our basic ideas here. All right, let's see what else notes we have here. The red forces formed a couple. The red forces were eliminated and replaced with the moment of the couple. The blue force remains and is now shown red in the rightmost figure. This is an equivalent force couple system, and we have effectively moved the force now. Notice these items. Force vector F cannot simply be moved without modifying its effect on the body by adding the moment. That's paying off the government with the moment. Okay? Attaching equal and opposite force vectors at O produced no net change on the body, And this is why this caused an equivalent force moment system. You got this? And we call it a force couple system. Okay. Here's another one. This is so if we want to take the resolution of a force into a force at O and a couple. Once again, we can look at here. So let's say we already saw that this force at point A, this is the same figure, the leftmost one. We have a force at point A, and it's where we were studying the effect about point O. But let's say we want to know the effect about point O prime. We want to now understand what does this force do about this other axis. Let's say that you actually did all this work calculating about the CG at point O, and that somebody added a little bit of mass, and now the CG of the part moved, or of the satellite, or whatever or the alien of whatever you're doing, right? So now we need to calculate a new force couple system. Well, we can either take the force that we started with, we can take this R prime, and we can see that it's going to be R prime cross F. Or we can use that force couple system we saw before. We can take S cross F plus the moment to get the final effect. We can use either approach. So if we move F from A to a different point O prime, we could look at it this way. We could say that the moment about O prime is just R prime cross F. Okay, that's old news. The moment of F about O and O prime are related. How are they related? Well, since M about O is R prime cross F, we can say, okay, that means it is R cross S, R plus S cross F, right? R plus S. If we look at this, we see, let's see, R plus S, R plus S. So if we start from O prime, we see R plus S is actually this vector R prime. Or you can say R plus S is just S plus R. That's the way it's drawn here. You'll notice R plus S is the same vector R prime as S plus R. So we see that R prime cross F is just R plus S cross F, which we can write as R cross F plus S cross F. R cross F plus S cross F, which we see is just that moment plus S cross F. That would be starting here. If we look at this guy over here, once again, we also had this F, and we had this moment, and this moment can just be moved. This is the moment about O. Actually, I'm doing the same thing there. Let's use a double-headed vector about it. O prime. We could say, well, and this is S, the distance from O prime to O. We see that it's just S cross F, both vectors, plus MO, which is the same thing as this, written in a different order. And that was deriving it from our old system. See how that works? So we actually don't have to go through couples to do that, but that is another cool thing that helps us to understand how this works. So moving any force couple system requires careful consideration of the moments generated. Let's look at a couple little examples here. This is a pretty classical example from Beer and Johnson. Here we see we have a system of pipes and we have a bunch of forces. And let's say we want to resolve this into a single equivalent set of couples. Now, you'll notice here a couple things. We have two forces of 30 pounds, and these are equal and opposite. That means they're a couple. They form a couple. We have two forces of 20 pounds, and these are equal and opposite. That also forms a couple. One forms a couple in the YZ plane, and the other one forms a couple in some skew plane. Now, if these were just forces, we could resolve the moment about any point by just taking, like, let's say we wanted the moment about point B. We could take we could take the position vector BC crossed with that first 30, plus BD crossed with the second 30 plus BD crossed with the lower 20 plus BE crossed with the upper 20. And that will give us the total moment about point D. About point B. If we wanted the moment about point A, we could take AC crossed with the upper 30 plus AD crossed with the lower 30 plus AD crossed with the lower 20 plus AE crossed with the upper 20. We can actually do this with less calculations if we start from point E, or let's even start more easily, point D. If we start with point D, then we're going to drop two vectors from the calculation. We can just do this by saying the position vector DC crossed with 30 plus DE crossed with 20 is the total moment on the system. Now, normally, if we just had a bunch of random forces, those calculations for moment about point B or A or E or D would all give us different moments. However, since in this case the only forces involved are couple forces, which are completely balanced by another equal and opposite force, no matter where we take the sum of the moments, we're going to end up with a single moment of the exact same magnitude, because since these are couple forces, they all cancel and only leave us with a single moment, which no matter where we calculate that moment about, is going to be the same magnitude. Es lo mismo. Okay? Another way to solve this would actually be to resolve the moments of this couple. When we take a look at this, we look at the 30 couple, the 30-pound couple, and we already know that the moment of a couple, the magnitude, is F times the perpendicular distance. We can see that the magnitude of this moment is going to be 30 times 18. That's the magnitude. And we also know the sense. We can do that by taking either one. You can use the right-hand rule, and we can see, oh, look, if we take the right-hand rule from the lower point, the D point, we see going toward C, wrapping our fingers in the direction of the 30-pound force, tells us we have a negative X moment is the resultant moment. So it's 18 times 30 in the minus I direction. Now the other couple is not quite so simple. It's going to be, you'd have to calculate the distance between them, which looks like it's 9, the square root of 9 squared plus 12 squared is the distance, times 20 is the magnitude. But now that the direction will be a little curious, because actually we have two, we could think of this as two couples. We could think of this as two 20-pound forces lying in a horizontal plane and two horizontal forces lying in a vertical plane. That would mean that it's 20 times 12 about in the positive J plus 20 times 9. And if we look at that, these two, 20 times 9, we've got it going like this. Oh, this was the 12. We already covered that. And now we've got to our 9 direction times 9. We're going like this. So we actually have 20 times 9 going in the K direction. You see that? 20 times 12 in the J plus 20 times 9 in the K. Let's see how that works, working out using Beer and Johnson's book. So this is that saying we're going to do that. We're going to resolve this into a set of couples. We have mx is going to be 30 times 18, and it's saying it's minus 30 times 18, right? Because actually we can see that we're going 18 up, positive, cross with 30 in the minus direction, right? But we're just calculating magnitude. We could actually just say, wait a minute, it's 30 times 18, and we can see from right-hand rule that's going in the negative I, which you can see there in the resultant. And then the other couple, both of the second and third terms from the second one, we've got this 20 times 12, which is giving us a plus J. And we've got 20 times 9, which is giving us a plus k. See how easy that is? And this is our resultant vector. We could draw it as a single vector as the resultant, like this, going out this direction, right? Or we can draw it as our 3 components as is written there. Okay. Here is, so let's think about what we saw. We saw all this, right? So our moment about D, we could think of this here as just taking the 18J crossed with minus 30K plus 9J plus, or excuse me, minus 12K, right? So let's work through this. This first term says if we're taking the moment about D, we're going to start with this position vector, 18J, crossed with minus 30K. We can see 18 times 30, right? And we can see this J cross minus K. J cross minus K is going to give us minus I, right? All right, now we're also going to take this other one. So we're going to have this, our position vector is this, going to that force. And this position vector is 9 in the J direction minus 12 in the K direction, and we're crossing that with minus 20 or plus 20 in the minus I direction. See that? So we have two cross products here. It's 9J crossed with minus 20I, which is 9 times 20, J minus I. That's giving us a positive Z. And we've got this minus 12 crossed with minus 20. So it's 12 times 20, where we're going minus K and minus I, which is giving us a plus J. Okay? As we see here. All right. Let's think about this a hair more before we abandon this study. Let's think about some practical examples. So let's say we have a beam. Beams are commonly seen in industry. In fact, if we look at the cross section of the fuselage, we got the skin out here, we got a floor beam, right? Let's say we focus on that floor beam. And let's say we have a force here and a force here. They're equal and opposite. This happens if, say, there's a galley or lavatory. Let's just say that actually we get an overturning load trying to blow it over the side. A lot of times that would give us a shear, but it'll also give us a moment. If these are the same magnitude, and let's say they're only 20 inches apart, we could say, oh, well, that is just a couple. Our moment is simply P times 20, and we can see that it is like this. It's the same thing as putting a moment like this. Or let's say we have a galley in a fuselage. Let's say we have floor beam here, a floor beam here, a floor beam here. All this is part of an aircraft. And we get, say, an emergency landing case where we're going 9 Gs forward like this. This is a very common case. And if this is all symmetric, we could say, well, let's say we have two attachments to the floor here and here. What this is going to end up doing, let's look at the side of this. We'll take a view looking from the side here. Once again, we're going to find this is forward now. We have this 9G force here, or acceleration. We're resisting here and we're resisting here, and these have an equal and opposite value. We can just call it R. And actually that R would just be whatever this force is. Let's say this is 10,000 pounds. 10,000 times this height divided by the distance between these guys would give us the magnitude of this R. But as this overturns, we see, oh, look, we get a reaction R. So this is just, this motion, this force is just giving us this couple, and this couple is simply a moment of RD. So we can actually figure, or if let's say we have a ball and the CG is here, and somebody puts a force out here at a radius of, say, 10 inches, say the force is 5 kips, we can see that the moment on the ball is going to be 10 inches times 5K. It's 50,000 inch-pounds. See that? It's that simple. When you understand couples, you can do a lot of really quick and accurate calculations with just scalar operations. Very powerful. Study this material. Be sure to work 5 to 10 examples from your book in this area, both for the simple scalar calculations, but also practice doing that R cross F over and over again. You're going to find it's actually not very hard. When you can do it proficiently, then you're ready for testing and quizzes, and you should master those. When you master this material, you're going to find out how fun this material can be. Enjoy.